we're going to be going over vectors. And then I left off last class on this slide. It's just some basic, good knowledge to have. Physics is a study of motion, so we are going to start looking at how things move. All right. So just like that last line of where I left off last time, if we're doing any sort of complex problems or equations, things can get messy. There's a lot of things that move on big everyday objects like a car or an airplane. Is hundreds, maybe even hundreds of thousands of small individual moving parts. So it doesn't even have to be like a special like wheel that's moving. It could just be like the left wing is over here and it's moving at a certain speed versus the right wing of an airplane is over here and it's moving at a slightly different speed. So that's what I mean by things can get complex. Just things that have size. So we take these big complex things and we just cram it all down into a single point. Usually it's in the center of that thing, or you can just, don't even worry about the picture at all. Just say it's a dot. Say this dot is a car. This dot is a bicycle. And go about the problem. Because the goal of, solving these problems is just, how can I make it easier to understand the concept? So I only want to look at the physics of these problems. So, say we have a bicycle. We're going to need to consider this bike just a single point. And I know that point is pretty large on these diagrams. Imagine just like a single particle, like an atom size. That's all we're worrying about. So, some rather big dots because it's for a presentation. We're going to need to know the displacement of that object or of that dot. Where did it move? That sort of leads into why we started, or brings back why we were learning distance versus displacement in the previous chapter. How has this bike moved? Well, it went from this position right here. I'm going to call the initial position. So I'm going to say x sub I for initial, or wherever it starts. And wherever that dot, or however you want to think of it, wherever it ends, that's the final position. X sub f for final. And displacement is just the difference between the two. So we take, typically it's written as a delta x. So that's like this Greek letter delta, it's just a triangle. Delta x equals final position minus initial position. So all that's saying is it's that wide, or that's distance. I guess maybe clarify like this. So whenever a problem says delta something, it's just final minus initial. Next, we're going to go over, things are going to be moving, and typically we throw around the word speed and velocity, and you might think they're the same. They're not quite the same. We have speed limits out on the roads, you have to take into consideration that whenever we say speed, we just mean the absolute value of velocity. So speed doesn't care which direction you're going, this way or this way. It's the same speed. That's why it's, I guess, a speed limit, because it's the same going either way on the road. If we want to find an object's average speed, so let me, this average speed, that's basically just how much distance did it cover and how much time. So and in the previous section with displacement, I was using the letter X for like how things move. I don't want you guys to use speed because we very rarely use speed. Oftentimes we want velocity because it says which direction we're going. Are we going this way versus this way? It's important in a problem where we're trying to find how a projectile is flying. When the answer, maybe the direction is wrong, the projectile is not going that way. So velocity is the main one that we're focusing on. So I'm going to abbreviate distance as equals s delta t. All right, so I sort of leaned into velocity. Let's talk about average velocity. This is why velocity is important. It's a vector. How do we find this? It's just the displacement over time. So let me do average velocity. Displacement over time. And so this comes back to that delta x over delta t. So the change in position over the change in time. So typically on like a normal stopwatch, the timer starts at 0. So the final time minus the initial time, or that initial time usually starts at 0. That's why we kind of might not worry about the time too much. But I'm still including delta t because maybe we're not starting the timer at 0. Maybe we want to look at the time range, in between 10 and 12 seconds for a specific thing. So then it would be final minus initial. So we have a average speed and average velocity example. There's going to be I was writing this up, I'm like, that's a lot. If you don't want to write all this down, you can just watch the recording later to get the exact details. I'd say maybe jot down the specifics for your notes. So the example is you're playing fetch with a dog, and you want to find the average speed and the average velocity of the dog. You just toss the stick, the dog goes running, and it goes out 20 meters. That is a good throw. So you are the origin for this problem. You are right at 0. You throw the stick, out it goes 20 meters. And the dog takes a specific amount of time to travel that distance. So let's write that down. So what does it say? The dog jogs 20 meters away. So it starts here, and it goes all the way out here. And I'm going to call, let's test, instead of me saying a final and initial, I'm going to just number these. So I'm going to say this is the first position, and this is the second position. So x sub 1, it's just a label, x sub 2. So it goes all the way over there in 3 seconds. And then it jogs back, but it's not, dogs never bring anything back perfectly. So it brings it back 15 meters towards you. So then it goes from this position back 15 meters to right here. So I'm going to call x3, so the third position. Okay. So total distance that the dog's traveled. So it's gone all the way there, all the way back, not all the way back. 20 meters there, 15 back. So let me write this out. Average speed that's going to be distance over time. Over time. And total distance, it's just 35 meters in how long?
7 seconds.
7 seconds. I made the numbers real easy. That is just 5 meters per second for the average speed. The average velocity is a little different though. So that is something a bit different. We need to consider where it starts and where it stops. So just like from the whole experiment. So right when you say go to right when we say stop. So right when the dog stops. So it takes, it goes from, we need to do x2 minus x1. So this is that first blue line I have on the top. So that's the first displacement over how long it takes to do that. And we need to also include the second displacement. x3 minus x2. Because final minus initial for that second path is going that way. And it takes 4 seconds for it to do that. So I'm going to do it in like red. So 2 minus 1, that's just 20 for this one. 20. 3, so 5 minus 20, it's negative 15. These are meters, meters. We get 5 meters in 7 seconds. And I've done this, what was it? It was about 0.71 meters per second. And you can kind of see that maybe we're not using the right velocity or a wrong version of velocity, because I sort of talked up velocity being so much better. Yeah.
What about common denominators? How do you add that across? Then why didn't you just use x3 minus x1 to get the 5 meters in the first place?
Oh, my bad. Let's see. Did I do that? No. You are right. Bam, bam, bam. I was thinking it's a little small. Okay. So, let's see. That's going to be 80. And 80 over 12. This is going to be 45 over 12. Negative. Not 2, 12. Okay, so then that is 35 over 12. I don't know what that is. It's probably about 2 or 3. If someone has a calculator. 2.9. Okay, so it's slower. It's like half to, it's around half of the speed. The thing is, let me say this, 2.9. We've done it right. Thing is, the average velocity is slower. And I was talking a lot about how velocity is better. But it seems like maybe using the average velocity doesn't quite include the full picture. Because it thinks we're only going from the beginning to the end, and it doesn't care about that other business of running all the way over there and back. So maybe the average velocity isn't great. So maybe a thing that can help you picture this is what if the dog brought the stick all the way back? All the way back to the origin, 0. So then it would have gone 20 meters, and then back, and then it hasn't moved at all for displacement, right? So maybe we're taking too big of a range for the average. All right, here we got just a position versus time graph. I'll say the people who have had lab already have a slight bit of advantage over those who haven't. So we have things that are going to be moving, and they could be moving at in different ways. I have like a bunch of toy cars here. So let's see. This, I believe, it should be moving at the same or a constant velocity. So travels at a constant velocity. And what does a constant velocity look like on a position versus time graph? Now, keep in mind we're measuring sort of how this thing is moving as time is continuously progressing. So if this object, let's say right here, this end of the table is 0, Like that. Like that. This end of the table is 0. And I start a stopwatch. This thing is going to be increasing the distance. So imagine the values on this meter stick are going to get larger over time. And it's going to be getting larger at a constant rate. So that's going to look like this upward slope. It's getting a bigger distance in a continuous amount of time. So, nice little chart. What if there's almost just too fast. What if the car is going a little faster? So, if the thing is moving, let's say slower, it's covering less ground in the same amount of time. So I would expect the slope to be shallower, maybe down more. But it's not covering much distance in the same amount of time. It goes a little faster. Sounds awful. Covering a lot of distance in the same amount of time. The line is going to be sharper, more steep. Oh, it's awful. Okay, enough of that. What about that flat line on the top? So this is the object's position.
Means it's staying at the same velocity for the same amount of time?
Not the same velocity.
The same speed?
No, not quite. Yeah.
It's not moving.
It's not moving. The thing was moving at one point. I gotta turn them on again. It was moving at one point, and it gets a specific distance away, and then it stops. But the timer keeps going, and it's still here. And the timer keeps going, and now it's a constant distance away. And maybe we can lead right into that other one. The other slope downward, yeah. It's going backwards. The distance, you imagine on that scale, I didn't put any actual values in there. The distance from the origin, the position, is getting smaller. So here's the origin. It's getting closer. It's a smaller value. And we are back at 0. Oh. Okay. So I would say on this graph, you can maybe sketch this out and say, sort of summarize what these are. So I'm going to say on this graph, so I'm going to say this region, we call number 1. I'm going to say, there's more room over here. I'm going to say region 1, moving with a constant velocity away from the origin. Or I'll just summarize it, moving with a constant velocity. That's good enough for this description. Region 2, that's when the object stops a certain distance away from the origin, but time will always continue the same rate. So 0 velocity. And region 3, I haven't even put it in yet. That is when the object is moving towards the origin at a constant velocity. Or I can say, no, I'll say it like that, yeah. moving constant velocity. All right. In your lab, you pretty much do something like this. These are fairly simple, and I was talking about average velocities. So, say this takes about 10 seconds to do. This whole thing from start to stop, and it starts at 0. I'm going to try to make this make sense. 1, 2, 3. Say it takes 3 seconds, and then it stops, and it waits for a while. I'm mainly focusing on that first region. Displacement, and what we were talking about with average velocity, was sort of only looking at the final and initial. What if I only wanted to look at the position here? And not the whole region itself. That's something a little bit different that I could maybe describe in this next slide. So average velocity, you can maybe put a note next to that, is it's a bit too general. We need instantaneous speed and velocity. Velocity and speed. So that's sort of the idea of, I don't want this big, final initial, big region, and I'm just sort of ignoring the stuff that happens in the middle. My example for that is, suppose you go on a road trip somewhere. You guys go to the beach, or wherever, and your average velocity might end up being like something like 60 kilometers per hour, or whatever. But for a fact you stopped for maybe like half an hour on your trip, and maybe some moments in your trip you sped. You went like 80, 90 kilometers per hour. So the average is sort of ignoring all that middle information. And that's maybe some of that information we want to keep. Yes. So this is called the instantaneous velocity, right at a single point somewhere. Oop. I see. I was supposed to fill that out. All right. There was a little bit of space. I can't go back, I figured. So I'm going to write what I was supposed to write on this slide. So the instantaneous velocity is actually just a sort of limit. You guys remember from math, there was when you take the limit of something as it goes to a certain value, to either go to infinity or to 0. The idea is we take the limit of sort of that big range of velocity, and we say we only want a small sliver. We only want a single point somewhere. And that's what we're going to say. I don't want to write this too incorrectly. So I'm going to go like this. I'm going to put up here. This goes on the other slide. So instantaneous velocity. That is the limit. I'm going to summarize a lot. That is the limit of delta x over delta t as delta t approaches 0. And then I guess the official way to write that, I'll put that right here. V of x t limits so what this form is saying, sort of that nice official math lingo, is saying I only want a small sliver of time. So as t approaches 0, I don't care about that big range, that big average velocity. I only want a small sliver. And that leads into this slide. Okay, awesome. So we have a way of finding a very specific point. Maybe I need to know where a rocket is right at 3.4 seconds. What's the velocity? Or maybe I need to know right where, how fast a tide is moving, right at a very specific time. This is just a very general. I just made a curve on a position versus time graph, and it's not a smooth, straight up line like that, and then a flat line, and then downward. It has a nice curve to it. Where do we start? We start right here. Initial time, and I'll say just sort of dot that in. And let's say we end the path right here, right at this other end. So if we were going to do the average velocity, that formula I just gave a couple slides ago, that would give us a straight line that would look like this. Between the two. And you can see that this is a sort of shallow slope. And I've shown that if things are moving a little slower, they'll have a shallow slope. So that's how we're getting like that shorter, or sorry, that smaller velocity when we take all of that information. We only consider the two endpoints. So I'm going to say the slope average velocity but how do we find the instantaneous velocity? That would be like if I wanted to know the velocity right at let's say, maybe a little more dramatic, something right here. How would I find the velocity of that? Well, if I had like a function or something, I could do the limit of it. But I'm going to just sort of simplify how you can find the velocity. Whatever that slope is, it's just rise over run, is the velocity. So the slope of where this dot is touching this curve, that's a tangent line that looks like this. So the slope of that dotted line is the velocity right at that moment. So if I write small enough, I'm going to say slope of tangent line equals instantaneous velocity. Okay. Let's see. Before I mess up. Okay, that's next. All right. So now that we know that the velocity is just the slope of wherever that tangent line is on a curve, we can then just like lay over a grid and find the rise and run of that dotted line, that tangent. And that will be the velocity. So the example I have for that is just like another very random curve. This doesn't correlate to anything. You guys could just make a random curve on your notes. And I want to find the velocity right at 4 seconds. So if I put a point right at 4 seconds, let me do blue, so that's the color of this. You say, well, on that average velocity, I had a range. I had a final and initial. For instantaneous, it's a single point. How can I find, the change of something of a single point? Well, that's where we just extend that dotted line out, and like I said, we're just physically graphing it. So I'm going to, let's do it in purple. See, I conveniently made it line up perfectly right at 8 and 5. So that's right where that crosses, right there. So finding the instantaneous velocity is easy as finding the slope of this. So it goes up, rise over run. It goes up 1 to 2 meters, and it moves over 1, 2, 3, 4 seconds. So that's how I'm able to actually find the exact speed right at some just random point. Typically, a problem will give you enough that you can do something like this. Or they'll just tell you, right at time 4 seconds, the velocity is this. And then you don't have to do this. All right. Just for like a little bit of going back over it, where would you say the velocity is 0? Since I said the velocity is related to the slope of the line, between what times is velocity 0?
5 and 6 seconds. Or it looks the flattest.
Okay, yeah, 5 and 6. I can maybe even push it to like 4.5, and maybe next to 7. Yeah, there's a good region in the middle where there's a slope of 0. So that means it's not moving. So 0 velocity. There's another one. Actually, there's 2 other ones. Yeah.
Your min and your max right there?
The minimum and the maximum. Just for the meter stick. Here's one. So imagine you're following that around with an actual ruler or something, finding the slope. So right at the minimum, right as it rounds that corner, there is a slope of 0. Same thing with that maximum. There's just for the briefest moment, there's a slope of 0 right on the top of that hill. Yeah, I think that's fine. Now we get to acceleration. Acceleration is a tricky term because it gets thrown around a bit too loosely, just like velocity. So I had originally, in like bold and like extra font, I said acceleration is not velocity. They are not like the same word. They do not mean the exact same thing. The acceleration is the change in velocity. So, how can I describe that? Let me see. I already got that. Let's have average. Okay. So I think the main thing to think about is you can always say what is happening to the velocity of the object at that moment. I have this sort of like big track out here, and I have this car that moves almost frictionless. It does slow down and stop, but it exhibits velocity, and just for a split second, some acceleration. Thing is, which is which and where is it? So, velocity is the object's movement or change in position. So right now, it's going that way. Positive. For you guys, that's negative. We're always going to consider, I'm just going to write this on the board. So, always going to consider things moving to the right as positive, things moving to the left as negative. And later when we get to 2 dimensions, we're going to say up is always positive and down is always negative. Maybe do that in a darker color. But I think you guys might already get it. Yeah, that's fine. So we have this thing that's moving. And if it was moving with a constant acceleration, I'm just going to move it gently with my hand. So it would be moving constantly at the same velocity until I stop it or whatever. So for you guys, this is positive. Now it has a negative velocity. It's moving that way. A negative constant velocity. The thing that maybe you could relate to acceleration the most is when you're sitting in your car at a stoplight and it turns green, you then have to accelerate to change your current velocity. So right at the stoplight, you are stopped. So what's the velocity of something that's stopped? It's not moving. 0. At the stoplight, you have a velocity of 0. But then you need to change your velocity. So changing your velocity is acceleration. So that's why you kind of get thrown back into the back of your seat. But then what happens when you get to, say, the speed limit, like 40 miles per hour? Do you feel pushed back into your seat anymore? Once you kind of stay at 40, the speed limit or whatever. So once you are then moving at that constant velocity again, do you have any acceleration? I'm going to restart. So acceleration is the change in velocity. So even though this thing is moving, it has a constant velocity. That means the acceleration is 0. And a way I can maybe try to bring that into light is like this spring. You think of it as the acceleration of the car. Maybe I could just, no, I'll go with this. So if we have a car at a stoplight, and that might be too light. I'll think about it. We have a car at a stoplight. It's not moving. It's not moving. I'm not accelerating. I'm not changing my velocity. The spring is unstretched. Zero acceleration. But I want to accelerate that way when it turns green. So spring is stretching that way. So it's positive acceleration to speed up the car or this little glider thing. Once you start, you go like way over here. Once you start speeding up and go at a constant velocity, it's no longer stretched anymore. So zero acceleration. Let me go to the other side. Let's say you then you're going on Herndon and you get all the red lights, and you need to slow down. You were going at that constant velocity, but now you need to slow down. You need to decelerate. So you're having an acceleration that is opposite to your own velocity. So this is sort of imagined as the spring pulling back on it. The velocity is this way, but the acceleration is that way. Until they cancel each other out, and we're at zero again. I will get that later. So the thing is just to always ask, what is the velocity doing in this problem at this moment? Is the velocity constant? Is the velocity changing? How is it changing? So we can find the average velocity. Average acceleration and instantaneous acceleration. And it's just the same exact thing. But this is acceleration, not velocity. So what will be the sort of the fraction I'm going to write?
Velocity over time.
It's velocity over time. So the change in velocity. The change in velocity and the change over the change of time. And of course, this is just, final velocity minus initial velocity is final time, initial time. And the same sort of, formal way of writing the instantaneous acceleration. I keep saying velocity. Limits as delta t goes to 0. So all of these steps, I did with position into velocity. It's the same exact thing going from velocity into acceleration. So that applies to the graphs I was talking about earlier. So I spent a long time making sure you guys understood what the graphs are saying, because it's the same principles with a velocity versus time graph. Same exact thing, except this is velocity versus time. So this is saying that the velocity is increasing, same amount of time, the same like intervals. For this middle region, the velocity is constant. And for that third region, the velocity is decreasing. Region 1, region 2, region 3. I'm going to try to simplify this since it's the same exact thing except with velocity in the wording now. So 1, nope. How do I phrase it? How did I phrase it? Increasing velocity. Velocity. Region 2. Constant velocity. Region 3, decreasing. Decreasing. Okay. That. I believe, I have, this is just sort of a, I think I just like, I'm going to give him a bunch of graphs. Just write the thing over on the left. So, slope of a position versus time graph is the velocity. You can see that we have some slower sections, some faster sections, some sections where we're not moving because the slope is velocity. I think I've made my point. Next, this is a different slide. There's a velocity versus time graph. So the slope of a velocity versus time graph is acceleration. See, they just feed right into one another. I was planning on writing sort of going over and over and over the same graphs. Okay. I think the last thing I want to talk about is, I try to put like moving pictures, like little diagrams and stuff, but in your book or somewhere else, you might need to draw it by hand and be able to actually picture something in your mind, because when you have a piece of paper in front of you, it's not going to move for you. You have to imagine what's happening. So I'm going to go over some motion diagrams that maybe you can learn how to draw or interpret. They're always good to be able to interpret. First off, we have something like a hockey puck that is on ice. So I think these cars work well. This one's too loud. It's moving at a constant velocity. You guys seen that? That's boring already. What about this? It's a little hovercraft disc thing. So something just like air hockey or skating on ice, you give something a little push, it'll start to move at a constant velocity unless it has friction or something that makes it slow down. So, as a constant velocity, every interval, it's moving at the same rate. Let's see what the little one does. Yeah, So moving at the same rate, just like a hockey puck. That one sounds great too. Okay, how do we like simplify these problems? Maybe I don't want to draw a hockey puck for all of my homework. So I just simplify it to a single point, a dot. And this is, I'm going to say it's moving with the velocity pointed that way. So it's positive. At that moment. And since it's frictionless, it's not being acted on. It's moving at a constant velocity. If I was to draw this to scale, all of these arrows, all these vectors will be the same size. So hopefully I can draw them all the same size. As a constant velocity, what is the acceleration?
0.
So the velocity is not changing, so it's 0. And I should be making these vectors. I'm just getting a little sloppy. Yeah, I should be. Let's go make them all a vector. Remember, acceleration is also a vector. Okay, easy. Next, we have a baseball. So I'm going to start on the left one, and I'm throwing a baseball up into the air. And imagine a photographer takes like a series of pictures, the same amount of time between each picture. It comes to a point where the ball reaches a peak, and then starts to fall back down. So we have maybe I don't want to draw a dot next to this. I'm going to run out of room. So I'm just going to say velocity is positive upward right here. And velocity is decreasing within the same amount of time, with the same interval of time, sort of representing that with the size of the arrow, the size of the vector. So that means that, I don't know if this spring example helps, but that means that the acceleration was opposing the velocity. So it was slowing it down, just like that, coming to a stop at a stoplight example. You guys don't like that example? Then maybe the picture will help. So this is an example of a constant downward acceleration. Later on, in the next lecture, I'm going to talk about Earth's gravity as a constant acceleration. So in all of these pictures, there's a constant negative acceleration. That is the same value. And I tried to make the arrows all the same size. And that continues, if I throw a ball straight up in the air, that acceleration is going to keep slowing it down as it goes up. And then once it reaches the top, the acceleration is still pointing down. And then it starts to speed up as it travels downward. So now the velocity over here on this side starts moving a little quickly. Negative velocity. Try to fill out this with vectors. A little bigger. And then it's moving very quick after a period of time because the velocity and the acceleration are both pointed in the same direction. So hopefully this is maybe a more clear example of when the velocity, acceleration, are together, pointing the same direction, we get an increase in velocity that way. When they oppose, that means we're going to slow down the velocity, and then we're going to change, however the acceleration is telling it to change. And the last example I have is like a car moving on the road. There's you driving down Herndon, hitting all those red lights. So we're at a stop over here, and try to imagine we're taking a picture, let's say every second. So 1 second right here. When you're at 2 seconds, you're right here, 3 seconds. So then you can see how much distance you're covering the same amount of time. So this moment, we are stopped. Velocity is 0. Acceleration is 0. But the light turns green. We want to speed up. We want to go. So we, how do I want to do this? Do it right here. We have a change in velocity that way. So that means we're accelerating that way. That, yeah, okay. Okay, then we get up to the speed limit, or at a regular speed we want to drive at, or we're comfortable at. And then we stop accelerating. We're going at a constant speed for a while. So we have a new velocity that is still positive, it's still going to the right, but we're not accelerating anymore. So the acceleration is 0. And we continue to move with this constant velocity for at least 2 more pictures. And we're going to try to make that the scale of that arrow the same. Since it's constant, acceleration remains 0. But then we hit the red lights. We need to start slowing down. We need to decelerate. We need acceleration in the opposite direction. So we slow down a bit. We still have a positive velocity, but our acceleration is opposite. Running out of room. So you see, they are countering one another, just like the baseball example above. And we keep going until we have a much smaller velocity. And we keep decelerating. We're basically changing our velocity just to make it slower until we stop. All right. So hopefully, I thought of this last minute. Hopefully this kind of makes sense. But it is sort of, when the two are pointed the same direction, we are going to be accelerating this way and moving that way. That means we're going to increase the velocity as we move that way. Same thing with this way. If they're both pointing the same direction, that means we're going to increase the velocity in this way. But when they are opposite one another, so say we're moving this way, but we start to accelerate that way, oppose the motion, that's when we start to slow down and stop. And then if the acceleration continues this way, then we're going to start moving that way. So it's just like that baseball example up at the top. ABC. I think that's all the demos I wanted to do. All right, so we'll pick up right here next time. You want to work? I know I didn't have office hours yesterday or today. If you have questions on the homework, you come down and ask. I'll work out some with you guys. But the homework's due before midnight tonight. Sometime I'll put up the next homework. They'll be due next Thursday. All right.